Welcome to the next lecture in electric circuit analysis. We were discussing the frequency response analysis. In the previous lecture, we covered the fundamental of frequency response computation using the transfer function method. In this particular lecture, we are going to focus our discussion on the Bode plots. So, how Bode plots are used to represent the frequency response and how they are plotted, that we are going to see. Generally, obtaining the frequency response from the transfer function is a difficult task. It is not very straightforward to obtain the frequency response from the transfer function. So the alternative way is a systematic procedure by which we can obtain the frequency response using the concept of Bode, who was the scientist who gave this method, is known as Bode plots. It is inconvenient to use a linear scale for the frequency axis as the range is very wide. So when we cover the frequency range, it is quite wide because we have to cover in the high frequency range like megahertz range or gigahertz range. So the linear scale is not suitable. So we will see that how the linear scale is converted to the logarithmic scale and what are their advantages. So we are going to use the semi-logarithmic plots. What are semi-logarithmic plots? The magnitude which is plotted in dB against the logarithmic of the frequency. So frequency is taken in logarithmic, whereas the magnitude is taken in dB scale. The phase is taken in degrees and that is also plotted as the logarithmic of the frequency. So in the logarithmic plot, our frequency axis will be in log axis and the magnitude axis will be in dB and the phase axis will be in degrees. So this is known as the logarithmic plot. And why the semi-logarithmic plot? Because we are using the semi-graph sheet to plot it, that we are going to see. Now Bode plots are basically the semi-log plot where the magnitude is plotted in decibel scale and the phase is plotted in degrees of the transfer function versus the frequency. So the transfer function is plotted versus the frequency axis where the frequency is the logarithmic frequency, and transfer function will have the magnitude as well as the phase in dB and the phase in degrees. So the Bode plots are easier to construct and contain all information as that of non-logarithmic plot. In the previous lecture, we have seen how we use transfer function to obtain the frequency response. In this particular lecture, we will use the Bode plot to construct the frequency response using the logarithmic scale. Bode plot will take the magnitude as well as the phase of the transfer function. We know that the transfer function is a complex quantity. So it will have magnitude as well as the phase. So here H indicates the magnitude and phi indicates the phase. And this is the representation of any complex number. If we take the logarithmic on the both side, what we are getting? Ln of h, that is on the left hand side, and the right hand side we will have the summation or the additive of the two different terms involved in the logarithmic. We know that natural logarithmic of the product of two numbers a into b is equal to the logarithmic of a plus the logarithmic of b. So the product is converted to summation or the addition in using the logarithmic. Here the term ln of h, which is the first part, it indicates the magnitude and it is the real part, whereas the phi which is involved in the second part is basically the imaginary part and it represents the phase. So the magnitude and phase are separated out. The j indicate the iota, which is equal to under root of -1. Now the gain we can obtain as h dB is equal to 20 log 10 h. So this we have already discussed in our transfer function concept as well as in the frequency response concept. So here the magnitude and phase both will be plotted on the semi-log graph paper. So in the Bode plot, the magnitude and phase has to be plotted in the semi-log graph paper. Magnitude plot again will be dB versus frequency. Frequency is in logarithmic scale. Phase will be degree versus frequency. Now, the standard form of the representation of transfer function. In order to obtain the frequency response plot, we need to know the standard form of the transfer function. So, the standard form of the transfer function, which looks like very complex, but it is made up of certain terms which we are going to see one by one. So, generally 7 terms are involved in the standard form. We can see a term k here which indicate the gain of the transfer function. Second, we can see a term j omega plus minus 1. So when we use the term minus 1 means in the denominator we have a pole and in the numerator we have a 0, that is j omega, and that is at the origin. So we have already discussed the S-plane in the previous lecture where we discussed the real part sigma and the imaginary part as omega. So origin is the point here. So if a pole or a 0 lies at the origin, that forms one of the factor. Now the third factor is basically a simple pole or a simple 0. So these indicate a simple 0 and these indicate a simple pole. So this is the third factor. The fourth factor is basically a quadratic factor having a pole or a 0. So we can see that a factor which is involved in the numerator of the transfer function, that is a quadratic pole because the power of 2 is involved, and we have a quadratic 0, the pole will be in the denominator and the 0 will be in the numerator. So quadratic 0 will be the numerator function roots and the quadratic pole will be the denominator root. So total term, if we add these 4 will make the 7 terms. So first term, second, third, we have the fourth term, fifth, sixth and the seventh term. All the terms may or may not be present in the transfer function. Now, in order to obtain the Bode plot, each factor is plotted separately. So one by one, we are going to take one of the factor and then add them graphically. So we will be adding them graphically to obtain the full Bode plot. Factors are considered one at a time and then combined additively as logarithmic are involved. So we have seen that how we are taking the advantage of logarithmic where a into b terms will be there and then we can convert that into the summation of two terms. So we have to add them when logarithmic are involved and each term will be taken one at a time. Now, this is a very powerful engineering tool, the Bode plot, because of the mathematical convenience involved with the logarithm. So, Bode plot has now become the industrial standard to represent the frequency response. So, the first term is basically the gain k, which is represented by 20 log k in the magnitude. So magnitude is 20 log k and the phase, if we see that it is at 0 degree. Both are constant. So if you see, both are constant and with respect to frequency. So here we have the frequency axis given in a radian per second. So omega is in radian per second, which is nothing but the frequency axis. So the gain, magnitude as well as phase are constant with 20 log 10 k and 0 degree. Now this is for the positive k. This is when the k is positive. If the k is negative, what will happen? The magnitude will remain the same. There is no change in the magnitude, but the phase will be plus minus 180 degrees. So here we have 0 degree and here we will have plus minus 180 degree depending upon how the k is present. Now let us take a 0 at the origin. So second factor we are going to take the 0, that is j omega at the origin. Magnitude will be 20 log. Now here you see in place of k we will have omega and the phase will be 90 degree. So we can see that at 90 degree there is a constant phase whereas the magnitude slope is at 20 decibel per decade, which is increasing, and the phase is constant with frequency. So the magnitude will be plotted with respect to frequency. So as the frequency is changing, 20 log 10 omega will change and the slope will be 20 decibel per decade. If you have a pole at the origin, then Bode plots are similar to the previous discussion whatever we have done, except that the magnitude slope will be minus 20 decibel per decade. Here we have 20 decibel per decade in zeros, but pole will have minus 20 decibel per decade and the phase will be minus 90 degree, whereas in zero the phase is at 90 degree. Now, if we have multiple poles, so if a term n is involved, for example, if we have two poles, then we have j omega 2 and three poles j omega 3. So if we have multiple poles, then the magnitude slope will be 20 n decibel per decade and the phase will be 90 into n degrees. So depending upon how many n are involved, whether it is a double pole, triple pole, so we can plot it with 20 n times and 90 n times the degrees. Now when we say 20 decibel per decade, what is the meaning of that? Let us define a decade term. What is decade? Decade is basically that interval between the two frequencies with a ratio of 10. For example, if we have 10 Hz and 100 Hz, if you have 10 Hz and 100 Hz, so the ratio of that will be 10 times. So 20 decibel per decade means that 20 decibel there is a change whenever the frequency change 10 fold times or 1 decade time. So 1 decade is corresponding to 10 fold. So 10 times we have change in the frequency. So 20 decibel per decade means there is 10 times change in the frequency. So the magnitude will change 20 decibel. Now the other term involved is simple zero, which is given by 1 plus j omega divided by z1, where z1 is denoted the zeros and the magnitude and phase, if we see, we can obtain that from this expression of the complex number, which is 20 log 10 and the magnitude of 1 plus j omega by z1. Phase will be 10 inverse of omega by z1. And then we can plot it with the magnitude and the frequency axis, the phase as well as the frequency axis. If we are plotting the simple zero, what we will be getting? So the gain HdB is equal to 20 log 10 and the modulus of 1 plus j omega by z1. We can see that with the reduction of the frequency tending to 0, we will get 0 value because 20 log 10 1 is equal to 0. Whereas omega, when it is increasing going towards infinity, that is a function of the frequency omega. So we can say that for a small omega which is tending to 0, magnitude is approximately at 0 straight line with a 0 slope. So first we will be having with a 0 slope line because of reduced frequency, and when the frequency is high or large, then the slope will be 20 decibel per decade. It means that at a certain frequency Z1, which is nothing but 0, there is two asymptotic line will meet and that frequency is known as the corner frequency or break frequency. Now let us see the magnitude plot. So this is constant with the 0 slope, and then we will be having a slope of 20 decibel per decade. So where the two asymptotic point meet, that is the 0 Z1, and that is known as the corner or break frequency. Now there are two plots, one is known as the approximate plot and another is the exact plot. We are basically going by the approximate plot method. So approximate plot and the actual plot are very close to each other except at the corner frequency. So if we see at the corner frequency omega equal to Z1, there is a slight deviation between the approximate plot and the exact plot. Otherwise, other part it is approximately and closely meeting with each other. So there is a deviation of 20 log 10 modulus of 1 plus j1, which is equal to 3 dB. So the deviation will be around 3 dB between the approximate plot and the actual plot. The same process happened in the phase also. There is a difference between the approximate plot and there is a difference with that of the exact plot. So if we talk about the phase now in detail, so phase is equal to tan inverse of omega by Z1. So we can see at the lower frequency when omega equal to 0 what is happening, omega equal to Z1 the corner frequency what is happening, and at higher frequency tending to infinity what is happening. So depending upon these values, that is 0, 45 degree and 90 degree, at different frequency axis or component, we can plot it the phase plot. So using the straight line approximation method, we can divide the frequency axis, that is the frequency below Z1 by 10, that will have the phase to be 0, and then at the corner frequency we will have 45 degree as the phase, and above 10 times the corner frequency we will have the phase to be at 90 degree. So here we can say that there is Z1 which is the simple zeros that is involved as the corner frequency, and then we will be going at 10 times below and 10 times up. So below that we will have 0 degree, and above that we will be having 90 degree. So here we have 90 degree, here we have 0, and between these axes omega equal to Z1, if you see it here, then we will have 45 degree. So that is the straight line approximation of the phase. Now on the other hand, if we have a simple pole, that is 1 by 1 times 1 plus j omega by p1, then the plots are again the similar except at omega equal to p1, which is the corner point. The magnitude slope is negative, that's minus 20 decibel per decade, and phase is also negative, minus 45 degree per decade. Otherwise these magnitude plot and phase plot will remain the same. Only difference will be the slope, the sign and the phase sign. Now talking about the quadratic pole, if we have a quadratic pole expression, which is the sixth factor we have, then what is the magnitude and what is the phase. So from here we can obtain the magnitude of the complex number, which is minus 20 log 10 modulus of 1 plus j times the damping factor omega by omega n plus j by omega n whole square, and the phase will be minus 10 inverse the imaginary part by the real part. So if I convert that into HdB, that is the gain, for omega tending to 0 what is happening, and for omega tending to infinity, that is very low frequency and very high frequency what is happening, then we can plot that and obtain the values. So when omega is very less, that is tending to 0, then we can see that the gain is close to 0. Whereas omega tending to infinity, that is high frequency, we have 40 log 10 omega by omega n. So here we will first start from the 0 and then we will jump, and then we will have minus 40 decibel per decade that will fall, and that is the approximate plot that we are obtaining, not the exact one, but it will give the quite good value. Whereas the phase which is at 0 degree first, and then it will fall by minus 90 decibel per decade. So the amplitude plot consists of two straight asymptotic lines. So we can see that first asymptotic line is here, and then the second line is here. So these two lines will be meeting at one point. So when omega is less than omega n, so here we have the omega n, below that we will have one with a 0 slope, and above omega n we will have a slope of minus 40 decibel per decade here, and that is for omega greater than omega n. Whereas omega n is the corner frequency for the quadratic pole. Now the actual plot will depend on the damping factor as well as the natural corner frequency. These two factors will define what is the actual plot, but we are not interested in the actual plot because it is very difficult to obtain that. Rather we are going for the approximate plot. The significant peaking in the neighborhood of omega n, if you see the omega n frequency and this the exact plot whatever we are seeing, that is depending upon the damping factor values, and that is added to the straight line approximation if a high level of accuracy is desired. If you want high level of accuracy, then obviously the damping factor and omega n will decide that, and we can obtain the high level of accuracy, but straight line approximation is good enough to obtain that. However, we will use the straight line approximation for the sake of simplicity. So it is always better to go with the straight line approximation because that gives the exact value and not very exact comparing the accuracy level, but obviously it will give the values which is very close enough, and it is the most easiest way to obtain the straight line approximation. Now talking about the phase, so phase is nothing but minus tan inverse of imaginary part by real part, which we are going to divide at the low frequency zone, that is omega 0, omega equal to omega n at the corner frequency, and omega tending to infinity, that is very high frequency what is happening. So when the frequency is low, then it is at zero slope. So we can see that it is at 0 degree at the phase. Omega equal to omega n, when omega n is there, then we have from minus 90 decibel per decade, and then at omega very high, if you take 10 times omega n, then we have minus of 180 degree, and between that there is a fall of minus 90 decibel per decade. The phase plot is a straight line if we see with a slope of minus 90 decibel per decade between the frequency of omega n by 10, that is 0.1 time omega n, and ending at 10 omega n. So between these two frequencies, we will have a slope decrease of minus 90 decibel per 90 degrees per day. Again, the difference if we see between the actual and the straight line plot is due to the damping factor. So the damping factor is the one which will decide the actual relationship between the approximate plot and the exact plot. So little bit there will be a deviation, and that deviation is due to the values of the damping factor that will decide it. Now notice that the straight line approximation for the quadratic pole are same as those of the double pole. So if we take the double pole or the quadratic pole, they will have the same relationship, because the double pole, when we say, is equal to the quadratic pole with a damping factor of 1. So if I take the damping factor to be 1, then the double pole and the quadratic pole are same, so that will be obtained using the straight line approximation. The quadratic pole can be treated as the double pole as far as the straight line approximation is concerned. So we are going to adopt the method of straight line approximation. So wherever the double pole is there or quadratic pole is there, both will give the same result. On the other hand, if you have a quadratic 0, then the plots are nothing but the inverted one with the quadratic pole, because here the slope will be 40 decibel per decade for the magnitude, and the phase will be 90 degrees per decade for the phase. So only the plot is going to invert, otherwise the zeros and poles will give the same nature of the plot. So this is the summarized one of the factor of the gain as the factor. Here we have the 0, that is the simple 0, and simple pole. We have how it is behaving. We can have the quadratic pole, and this is the zeros and pole at the origin. This is the 0 and pole, and so this one will have this simple pole, and this pole and 0 will be the zeros and the pole at the origin, and then we can have the quadratic pole and the pole also. So these represent the quadratic zeros and the quadratic. We can obtain the magnitude plot, and we can obtain the phase plot step by step in a systematic procedure, and then we can obtain the graphical connection between that. We will solve one problem to understand the Bode plot. So construct the Bode plot for the given transfer function. So this is the transfer function which is given to us. We have to obtain the Bode plot for this transfer function. First, we will convert that in the standard. So standard form is having all factors that are involved in the transfer function in the form that is given in the standard expression. So here we can see that we have converted 1 plus j omega by 2. This expression which is having the poles, this expression which is having the pole, we have converted 1 plus j omega by 10, and then correspondingly our numerator will be changing. Now we will convert the magnitude and the phase. So this is our magnitude quantity and this is our phase quantity. So magnitude and phase we have obtained. So the magnitude and phase we are going to plot separately in a graphical procedure one by one. So first we have to convert that in HdB, which is involving the logarithmic of the different factors. So here we have the factor 10, which indicate the gain. So that is 20 log 10. Then we have the factor j omega, that is a 0 at the origin. So 20 log 10 of j omega. And then we have the two factors which are nothing but the poles of the transfer function. So that two factors we have obtained and we have taken the magnitude to obtain the magnitude one. And this is nothing but the phase. What we have to observe is that in the phase quantity we have two omega point, that is 2 and 10. These are nothing but the corner frequencies, which is 2 radian per second and 10 radian per second in the phase quantity. So the magnitude and the phase can now be plotted step by step in the graphical procedure, connecting the gain, the 0 at the origin. Then we have the two poles one by one. We have to add it graphically to obtain the magnitude in dB and then the phase in degree with respect to the frequency omega. So we can see that the corner frequency will be at omega is equal to 2 and the corner frequency will be omega equal to 10. So there the deviation will be there. So first quantity we can see that 20 log 10, which is a constant with 20, and then we have the factors involving, which will be involving the factor of 20 decibel per decade, 40 decibel per decade, and so on, depending upon what factors are involved. So these we have discussed one by one how the graphical procedure it will be added. So we have to add the factors and then obtain the plot. So here we will be having a 90 degree, then it will be a fall, and then it will be a fall, and then we will have minus 90. So magnitude plot and phase plot we are going to obtain. So here in this particular lecture we have discussed in detail the Bode plot, obtaining the magnitude and the phase response of the transfer function, and in the previous lecture we have discussed how the transfer function itself can be used to obtain the frequency response. In the coming lecture we are going to discuss the resonance condition, series and the parallel resonance. So thank you for now.